Hello everyone. In this video we're going to recreate the famous Piere Luigi Nervis example where he creates the downstanding beams on this floor slab using the principal moment lines. Our basic system is a column and a slab, and for the basic Karamba analysis I won't go too much into detail because you can download the definition from our repository. And we have a lot going on at the end of the definition. So the main thing here is we want to mirror this system later on. So we set support points at this and at this edge with different degrees of freedom selected. So it acts like if we mirror it in this direction and in this direction, it will act like a single slab. So we have our analyzers, and as you can see, if I activate this, the deformation looks a little bit asymmetric because there and there are supports simulating a continuous slab. So we now take the Karamba model, our calculated model, and want to generate the principal moment lines on there, first in this direction, which means the circular principal moment lines, and with this component the other direction from the inside to the outside of the plane. For the first case we use a line generated from the upper point of the column to the edge of the slab, and this line gets subdivided into 4 points. We will use as our seed points. So here in this container is our calculated Karamba3D model, and we put it into the line results on shell component. As you can see, with these results we have a little bit of a problem here because the curves running around in circles multiple times, and we don't want to use these lines at all. So I disable this preview, and for the circular lines, these are the lines from the second line output. We just need to take them, and we want to join them to a single curve. And another important thing about the lines output here is Karamba sorts the line in data branches, because if you have a point here going away from there in this direction and another one in this direction, so you have two lines which are basically one line but in two directions. So first we join those into single lines, and then we need to shift the data tree into these single branches and then join them again, so they become one continuous line. So to get rid of the multiple circles here, we use the first segment of each of these curves at the start point, and we create a perpendicular plane to the first segment, and then we intersect the segment with the single lines, and with that we can then later split the segments into just the section we want to have from the curve, which is going from this point one full rotation around and back there. And then we have to rebuild this curve using, because as you can see we have a lot of points here, and first of all we call the last point, so the result will be a little bit smoother, and then with this component we only select every nth element of the list, so we reduce the point count with that, which helps, or which makes processing later on a little bit faster than just using 200 segments instead of like 20. So, and the results from this process can be viewed with the custom preview component. And as you can see, they are relatively coarse polygonal lines for the first direction. So the second direction from the inside to the outside is generated here. For this, we generate a circle with the center point on the top point of the column, and again divide the circle into 10 points. So now this component uses these points as seed points and generates lines from there. So as you can see, more or less the same problem as we have above, but now we only want to have these lines for our next steps. So in this case, we use the upper line output. Just visualize it. Yeah, and now we only want the lines going from the point outwards. The thing is, I told you Karamba sorts the points in the two directions from where the lines are drawn. But in this case, we can try to use tree statistics to extract the paths. And select them using the tree branch. But as you can see, Karamba doesn't know from in which direction it draws the lines because there is no up, down, left, right. So now we have the problem that we have lines coming from here, starting in this direction, and but we want this line. So for that we have this little C# script, which just dispatches the branches if the point on the first segment of the branch is inside of the circle. So if the point on the first segment is inside the circle, it gets culled out of the list, and only the other list gets put into the new branches, which are called output 0 and output 1. And this is the standard Rhino function for evaluating the position of a point inside a curve, if it's inside, outside, or on the curve. So we have now two outputs, A and B, which corresponds to output 0 and output 1. If I now visualize it, A are the outputs that where the first segment starts inside of the circle, and B are the curves going outwards. So from here we have the same procedure as before, joining the curves and then rebuilding them as above. And the second, or this extra part here, as you can see, because of this component where we call out the parts, or we just take every 10th element, every 10th point, we are missing the points going straight to the edges, so I just pull them back to the original rectangle and add them to the list. So now we have those points coming from the center of the plane to the outer edges. So now we can reconstruct the downstanding beams, which we already did earlier in an earlier video. I think it was number 26. And because we already did that, I just created a grasshopper definition which can be loaded as a hops component, which does exactly the same process we did earlier. So, and what this hops definition does is it takes a Karamba model serialized because hops right now can't input other data types than primitive ones, like points, curves, surface, text. So we input the model as a text. We input the surface, like this red surface, the basic floor slab. Then we input the curves, the orange and the blue ones, the beam height and the beam width, which are the cross-section values for the downstanding beams, and additional inclusion points, which are in this case the new support points holding the slab on this side and on this side. So if we take a look how this hops component works, I switch to the other grasshopper definition. And this is orange and red because I don't have contextual input given that this input block. But here are our inputs, which you can see on the hops component in the other definition. Here the Karamba3D model gets deserialized back into a Karamba model and then gets deconstructed, so we have the basic elements we want to reuse, again in our new analysis with the downstanding beams. And this is the new part where our principal moment lines get projected onto the surface. The surface gets split. We use the naked edges as downstanding beams. And the rest is, like in the previous video, the same building of the assembly and analysis. So the model gets then analyzed and again output as a serialized Karamba3D model. So if I look at the output, we get the serialized model again. And then we have to deserialize it again and calculate it because the C# model in Karamba does not include the calculation because it would be too bloated then. And we can look at the results with these two components, which does not look too bad. And how this hops component also works is you need to specify a path where this grasshopper definition is located. Either it can be on your hard drive or on a GIF. And how this works, you open your browser and go to the repository, K3D tools. There you find a folder with TidBits, and there I've put the hops definition. You can load from there, but also if the link is included in the grasshopper file, it should recognize it. And if you want to add another hops definition on a repository, you click the grasshopper file and on the download button with the right click and say copy link address. And then you can just use a panel and copy the link address, and it should automatically load the component. And at the end, we just have to mirror it with the planes we first defined, and then look at our result. In an upcoming video, we are going to talk about how to optimize the distance between each rib and also the position where the column pinches through or wants to pinch through the floor slab. Thanks for watching. Bye.